Welcome back. Nice to see you again. Trigonometric equations. Hey, what's that about? I guess you can see that maybe it's an equation with a trig function in it. Maybe something like this. And there'd be a few different ways you could try to solve all the possible values of x, such as sine x equals a half. What will we do? Well, look, have a look at this. That's a little bit of technology there. Drawing the graph of y as a half, drawing the graph of y equals sine x, finding where they intersect. That would be a good technology way, perhaps, of solving that. Okay, can you see that on the calculator? Graph the two functions separately and then find their points of intersection. On the Casio, we're going to talk about that in a minute, you would use Shift F5 to G-solve that, graph solve that. Quite clearly, we're going to have to remember some of these values we had before if we're going to solve these equations without technology. And then finally over here, this is why we're going to do it really, and that is because if we had a model, and this could be a model of anything, this is just y and x here, it could be tides or something like that. Tides are periodic, aren't they? We talked about that perhaps a little bit before. And we could find when the level of the water was at 12.5 metres or something like that, and have a little function, which is a model down here. Y and x could mean depth of water and time there. So in modelling, we will want to solve problems like when is the quantity at a certain value. And we're going to be able to, after this unit, do that with technology, or what we call analytically, when we just use algebra. So come on down and have a look at the technology way of solving these first of all. So if you're in a paper where you're allowed to use technology, that's paper 2, not paper 1 as it stands at the moment, then you'd be able to do this. So let's have a look at the steps. This is on the Casio, and here we have the graph mode entered there, and we've put in sine x and y is 0.5. So we would adjust the view window here. I've gone from 0 to 2 pi. I put in 2 pi on the keyboard, but it changed it to a decimal. So I'm looking at the graph of this function from 0 to 2 pi. And of course, you know what that looks like by this stage. It looks like this. And therefore, you're going to have a graph of sine x and a graph of y equals a half. And we can see their points of intersection in the domain of 0 to 2 pi. And so how do we do it now to find those points? We're going to go Shift and G-solve is up there, so Shift F5, and we get this window here, and clearly we want the intersection. There it is there, so you hit F3 and up pops a little crosshairs on the first point of intersection, and we can read that off there. Difficulty with technology, that's not the exact answer, is it? 0.52. What is the exact answer for the first angle in the domain 0 to 2 pi where the sine is a half? Do you remember? It should remember that. This is actually pi on 6. So this is one of the disadvantages of technology here. It doesn't give it to you in exact form. It gives you in the decimal approximation to pi on 6, which is that. And then, of course, if you scrolled across the screen to there, it would pop, the crosshairs would pop on the next point of intersection. And I wonder if you know what that is for a sine of a half. It's 5 pi on 6, isn't it? And it will come out as a decimal here. So that's the way we would handle it with technology. Draw the two graphs and then solve it with G-solve. And we could extend the domain in either direction depending upon the problem. We'd come back here to the view window and adjust that. So remember, the view window is Shift F3 to bring up this window here and adjust it. So we'll be practicing that a bit later on. You can check all your answers with technology. I think that's a good idea, so that you have a bit of practice there. All right, let's have a look at it a little bit differently. Let's have a look at it what we call analytically, or the algebra. So here's the problem that we just did with technology, and you can see we're saying we want all the solutions from 0 to 2 pi. So what is the process? And I want you to try and remember this process for harder trig equations that we have later on. Obtain an equation for a single function, for a single trig function. What that means is we just want sine x equals something, or maybe sine 2x equals something, or cos 2x. We don't want a mixture, sine 2x plus sine x equals. We would have to simplify that. Or cos squared x plus cos 2x, all this sort of thing. We would have to simplify these, and we're going to look at in the next presentation some ways of doing this with trig identities, the last part in this topic 3 of the IB. Anyway, so this is what we want, this sort of thing. It doesn't matter if there's a 2x there, we're going to learn how to handle that, but we do not want mixtures of sine 2x and sine x. We're going to have to do something with those. So that's the idea of that first step. Okay. Find the working angle. We're on to the second step now. Find the working angle, the angle in the first quadrant, which has the same size trig function value. Okay, that's a lot of words. Let's go and draw our unit circle. So sine x equals a half. Our working angle is the first angle in this quadrant with a sine of a half. It doesn't matter whether in the equation we have positive half or negative half, the working angle would be the same. So it's going to be pi on 6 here. We're going to have pi on 6. Why do we start there? Well, we know that we can generate equivalent positions in any other quadrant with the same size sine. Okay, and then what we're going to do, let's read this one now. Find equivalent positions in all other quadrants where angles will have the same sine of that sine or cosine or tan. The same sign. We want a positive. Use a unit circle to assist. Well, let's go back up here. Now we want all the angles on one revolution from 0 to 2 pi, which have a sine of positive a half. Where's the next quadrant where the sine is a half? It's that one. So we've got to create our angle back there, having congruent triangles so they have the same sine, and so this angle effectively, remember the sine is a y value of that point rotating around the unit circle, so this angle would be 5 pi on 6. Okay, we did a lot of that before. So are there any other quadrants here and here where you can get an angle whose sine is positive a half? No, because here the y value is negative down in these quadrants, and we want a positive half. Okay, so what have we got so far? We've got x equals pi on 6 or 5 pi on 6. Okay, continue around the circle in either direction according to the stated domain. Well, would we keep going? Let's say they allowed us to go to 4 pi. We go around another revolution. So our answer would be this: x equals pi on 6 or 5 pi on 6, but we could add k lots of 2 pi. They're going to repeat themselves, and k is a member of the integers. Okay, so it could be positive or negative. If we went around, let's do it here, if we went around the circle here, that's pi on 6, that's one we want. Let's say we went around neg 2 pi, right around there, we'd be back to that point. Okay, or positive 2 pi, we'd be back to that point. So we have a whole family. Remember the periodic nature of sine, cosine and tan. So the period of sine and cosine is 2 pi. If we go 2 pi further on, either positively or negative, we'd be back to that same spot. So this is our general solution here. Adding on positive or negative integers. Let's go back there. Positive or negative integers. Okay. So then we find the final angle expression, and we already have that. So we won't be going around again, it'll just be these two. So they are our answers. These 2 points aren't clear with this simple example, but they will be if, for example, we had sine 2x, because 2x would be equal to pi on 6 and 5 pi on 6. We'd have to divide the angles to get just x. Okay, so we're going to see that in a minute. But that's basically your, if you like, a template for a solution there to check that we're getting all possible values. Okay, let's go down and have a look at another one. Okay, so here's one here. 2 cos x equals -1. Our first step is to get an expression just for cos x. So let's divide both sides by 2. Cos x equals -1/2. Our next job is to have a look and see, don't worry about the -1/2, we want the working angle. An angle in the first quadrant whose cosine is a half, just a half, that's a working angle. So the working angle equals, now what angle is that? Do you remember? A cos of a half is the angle of the arc here, pi on 3. The cos of pi on 3 is a half. So the working angle is pi on 3. Now we've got to go around and find all the quadrants in which we can have an angle whose cos is -1/2. So we'll say our angle here, x, could be, yes, in this quadrant cosine, the x value is negative. So we'll have a congruent triangle there, and this will be, if that's pi on 3, this will be 2 pi on 3. 2 pi on 3. Okay. And then, of course, if we come into this quadrant, x is still negative. This time that's pi on 3 past pi. Now, do you want to see the best way of adding on and subtracting around pi's? Pi is 3 pi on 3. If you're working with an angle of pi on 3's, forward and back. Pi is also, 4 pi on 4. If you're working with pi on 4's, or 6 pi on 6, if you're adding or subtracting a working angle of pi on 3, pi on 4, pi on 6. So pi on 3 past here, pi on 3 past pi is 4 pi on 3, because pi is 3 pi on 3. And then we must put k plus k times 2 pi, meaning that if we keep going around, whole integer values of 2 pi in either direction, we'll be back to the same point. Now again, this is an easy one because you only go around once. So our solution is, in that set, 2 pi on 3 or 4 pi on 3. We state our answer. So that's a fairly basic one also. Let's have a look at some others now. You're getting the hang of this? Hope so. These screen clippings now are from a text printed by Hayes and Harris, and that's a handy book as well as Pearson's. We're using both of those now. So here is our problem. We're going from 0 to 3 pi for these three. They look a little bit different. Here there's a 2x, and x take pi on 6. So let's see if our method works. So first of all, there's our statement, sine x equals -1/2. Here's our unit circle. What they haven't put in is the idea that you'd go with a working angle for a start. And the working angle whose sine, just worry about the half, don't worry about the negative, the working angle whose sine's a half is pi on 6. That's your starting point really, not stated here. Then because it's a negative over here, you have to go into these quadrants where the y value, or the cos of the point rotating around, P1, P2, is negative. So this is going to be pi on 6, and so is this. So what is that angle? Pi plus pi on 6, 6 pi on 6 plus another pi on 6, 7 pi on 6. What's this angle? It's back pi on 6 from 2 pi. Well, you can do with 2 pi the same thing. 2 pi is equivalent to, 12 pi on 6. Or what you do it in pi on 3's, 6 pi on 3 to make it easier to subtract and add your working angle, and 8 pi on 4 if you're working with pi on 4s. So this position here is actually the big angle around there, which is 12 pi on 6 take pi on 6, or 11 pi on 6. That's not a bad trick. So there we have our two angles in the first revolution, plus k times 2 pi. But looking up here, we're actually allowed to go around another half a revolution. So let's see what we can do. K is an integer. So there's our first two. If we make k is 0, then you're not adding any two, that's those two. If you add on one more revolution, that's 2 pi, which is, remember, 2 pi over here is 12 pi on 6 if you want to stay in pi on 6 land. Then it's 19 pi on 6. That's gone past 3 pi, because 3 pi would be 18 pi on 6. So we didn't make it. Another half a revolution around here to get to 3 pi doesn't pick up another angle. So there's only two solutions. The book here is saying substituting in further multiples of 2 pi in either direction will give answers outside the domain. But we must try to go around in both directions to see if there are any more solutions. Alright, let's come down to part B. It's getting a little bit different now. Sine 2x is -1/2. Now, solved exactly the same way. So you have your working angle, put that down, working angle is pi on 6. You then go to the same two quadrants. What's the difference? The angle now is 2x. So the rest of it remains the same, plus k times 2 pi. Now, dividing both sides by 2, we've got 7 pi on 12, 11 pi on 12, and dividing that by 2 is k pi. Do you want to do some maths now? Why is that come to k pi? Well, if 2x is up there, and these values are having a period of 2 pi as we go round and round, x is going to, if you like, effectively have k pi, because you're dividing by 2. Alright, so let's see what we can do now. We are allowed to go from 0 to 3 pi. Okay, so here 7 pi on 12, 11 pi on 12. Then let's add on one lot of pi. A pi is 12 pi on 12, right? There's the trick. If you want a certain fraction of pi, convert pi to that, 12 pi on 12. So add 12 pi on 12 is 19 pi on 12. Add 12 pi on 12 to this one, we're doing these two, and adding them up. And then we can keep going. We keep going around the unit circle until we get to 3 pi, and that's it. Now, we've not gone negatively here. Why? Because there are no negative values in the allowed domain. Here they say don't forget to try k equals -1, -2, as sometimes we get solutions from them. We won't here, because if we subtract here from our first value 12 pi on pi, we'll get -5 pi on 12, and that's outside the domain. So it's a little bit tricky, that last bit there, of really making sure we get all values in the given domain. Okay, let's have a look at the bottom one now. This is solved in the same way. Can you see what they're doing? Just changing the angle in here. So the same thing, you see a half. Okay, let's just do it again. You see a half, and you always work out the working angle in there. Working angle for sine of a half is pi on 6. Then you take on board the negative, and you go to your quadrants where it is negative, which is again 7 pi on 6, 12 pi on 6, plus k times 2 pi. The process, of course, has a period of 2 pi, one revolution. You're picking up one revolution's worth. Now, this time, however, the angle was not x. It wasn't 2x either. It's x take pi on 6. So now we have to solve that. Add pi on 6 here. So that becomes 7 pi on 6, and 11 pi on 6 plus pi on 6 is 12 pi on 6. Remember, because pi is, what do you want? 6 pi on 6. 2 pi is 12 pi on 6. If you're working with fractions of pi, this is a good trick. to express pi itself and 2 pi as those fractions there. And we've still got plus k times 2 pi. Now, we're going to go around positively and negatively. So let's have a look. 8 pi and 6 cancels to 4 pi and 3. So we've got those two as our first revolution. That's k is 0, adding no more 2 pi's. If we go around one revolution, we're adding 2 pi. Let's add 2 pi to this. 2 pi, remember, is, here we are, 2 pi is equivalent to, what are we doing? Pi on 3 is 6 pi on 3. So adding 6 pi on 3, yes, that checks, 10 pi on 3. 4 pi on 3 plus 6 pi on 3, 10 pi on 3. And then that's too big, so we get rid of that. We better check a negative one here. Because we've added this pi on 6, we better check going backwards a bit. So if k equals neg 1, we take off here 2 pi, okay, which is 6 pi on 3. Okay, so if we take off 6 pi on 3, what do we get from each of these? Nothing there. Taking off 6 pi on 3 from here. Right, taking 6, we better do this properly. Taking 6 pi on 3 from here, 4 pi on 3 takes 6 pi on 3 is neg 2 pi on 3. Don't get anything there. But if we take 6 pi on 3 from here, this is 2 pi, is 6 pi on 3, take 6 pi on 3, we get a naught. See, that's a tricky solution. So it's actually got 3 solutions. So don't forget this hint up here. Take them away too, particularly when you've done this. See that? We've added pi on 6 there because the angle had x take pi on 6. So that allows us a bit more flexibility, I suppose, in working with the domain from 0 to 3 pi. It's a tricky little last bit there. Okay, are you ready? I've got some for you here. Well, there they are. Okay. So I would suggest you do all of these. Watch the domain. Look at this one. Neg 2 pi to 2 pi and neg 4 pi. Neg 3 pi to 3 pi. We can spin around both ways. So remember your solution, which is plus k times 2 pi. But k could be 0, 1, 2, etc. But it could be going back the other way to pick up those equivalent positions, neg 1, neg 2, etc. Okay. Are you good enough? Now, just down below here, there are the solutions. They're not fully not solutions, sorry, they are the answers. So you're going to have to work out how they got those answers. So come on down, we'll pause it now, and then come down and you can flick back and forwards to check your answer as you go. Make sure you do check it as you go, so that if you're making some fundamental mistake, it comes out and you can fix it, maybe need a teacher there, before going on to another one. Don't do them all and get them all wrong. Okay, here we go. Let's have a look. Here are the answers down here, which you can flick to and fro with, and just check that you get all of them. Remember, k can be 0, 1, 2, etc. or, no, it's not or, is it? It's and check neg 1, neg 2. Okay, right, we'll toggle back now and have a go at those. I'm going to move on. Okay, we've been doing just sine, sorry. Here's the cos, and look at the changes. We've got some changes in here. Okay, and a plus 1. So what's the first step? You must get an equation with a single trig function in it. So let's get a single trig function just by itself. So we have to rearrange it, subtract 1 from both sides, get rid of the root 2. So we just get a single trig function cos by itself. A single expression equals neg 1 on root 2. Now, our idea here is we must have memorised those values for the common angles here. Do you remember that the cos of pi on 4 is 1 on root 2, and that is probably better written, watch it, multiply top and bottom by root 2, that's better written as root 2 on 2. That is the simplest mathematical form, that third form there where you have an integer denominator. But anyway, recognising that form or that form. So the first step is to go to your working angle. They are not putting this down here. The working angle is pi on 4. So you know that the base angle there that has that sign is pi on 4. We now have to make up coses this time with negative values. So whereas cos negative, whereas x negative, there and there. So these working angles back here are pi on 4 and forward pi on 4 to produce the congruent triangles. Oh, that should be up there, shouldn't it? Which have the same heights here and widths here, if you like. Okay, so what is that angle around here? Pi, which is 4 pi on 4. Take pi on 4 is 3 pi on 4. And what is this angle right around here? It's pi, 4 pi on 4, plus a pi on 4. Just please remember, when you're working with pi and 2 pi, think of pi as 4 lots of that fraction, and 2 pi as equivalent to 2 lots of pi, which is 4 pi on 4, so 8 pi on 4. Okay. Alright, so don't forget to make your statement. And don't forget that your angle is whatever's in the bracket there. Watch for all these changes now. Okay, now, what are we going to do? Remember, add 3 pi on 4 across there. So this becomes 3 pi on 4 up the top, adding 3 pi on 4, 6 pi on 4, cancels 3 pi on 2. 5 pi on 4, add the 3 pi on 4, is 8 pi on 4, or cancels 2 pi. But now we can go around 2 pi. This, oh, look at this. Didn't look at that before. Look at that. 0 to 6 pi means we can spin around 3 times. So let's do k is neg 1. Okay, so if k is 0, we've got the 2 base values. If k is neg 1, we can take off 2 pi, and if we take off 2 pi from here, we get neg pi on 2, or 0 from here. Okay, if k is 0, we get our base values. If k is 1, adding on here in pi, well, what's our answers? Pi on 2 and 2 pi. Adding one lot of 2 pi, this comes to 4 pi on 2 plus 3 pi on 2 is 7 pi on 2. This comes to another pi, 4 pi. So we are allowed to spin around, watch this up here, we're allowed to spin around 3 revs if you like. So there are going to be more solutions. If k is 2, we add on 4 pi, 2 lots of 2 pi is 4 pi to this thing here. 4 pi will be 8 pi on 2, that's giving 11 pi on 2. And 4 pi on the other one is 6 pi. So there's lots of solutions. The only one that doesn't work is neg pi on 2. Just remember, k equals neg 1 and neg 2 have to be checked, because otherwise you don't pick up what solution there? That one. It's the only one you wouldn't have picked up. So that's a little bit surprising. Let's go back up there. Let's pop down. That's a little bit surprising. It's because of this adding on of 3 pi on 4. Okay, so that actually all of those solutions there, we haven't checked 3, k is 3. But that's adding on, k is 3 is adding on 6 lots of pi, and that is outside our domain, given that we have values non-zero already. Alright, okay, so let's go down and see what you think of these. This is all in cosland. Okay, you can do the same in sines. There's a few variations there for you. So what's the domains here? There's some negative values there. Okay, I want to talk about this last one, about how you might write this one in terms of a single trig function. Let's play with it a bit. Let's get all terms across to the left here equals 0. Do you remember why we might do that? Why is 0 special? Well, if we can factorise the left-hand side here, we can use a null factor law, which says if you have a product of 2 functions equal to 0, one of those 2 must be 0. So it gives us a method of solution. That's reasonable, isn't it, the null factor law? And you're multiplying 2 things together to get 0. One of them must be null, or 0. So can we factorise this? 2 cos x, cos x. Can you see what I'm doing? I'm taking this as a quadratic function in cos x. in cos x. So here, what will I have? I'll have neg 1 there and plus 1 there. Does it work? 2 cos x by cos x, 2 cos x squared. 1 by neg 1, neg 1. Then the middle terms, that's neg 2 cos x plus cos x. Here it checks. Now if you don't like that method, you could let p be equal to cos x, and then it becomes 2p squared take p take 1, and you might find that easier to work with. So here you might find that easier to work with, as I was saying, and it would look like this, and then you could go on there replacing p at the end with cos x. Okay, think about that. Well, how would we solve this then, done either way? Well, from here we'd say 2 cos x plus 1 is 0, or cos x take 1 is 0, and go on from there. So that would be a big one. There'd be two separate trig equations when we get those isolated by themselves. So just remember, with a quadratic like this, we must get single expressions in cos here. Can't deal with this very easily. So there's a lot of maths in that one. We're going to go on now and do some of those with signs as well. But for the moment, I'd like you to try those 8 problems and see what you think. And the solution is just down below. So I'll show you the solutions, then you can come back one by one and do the problems and check the solutions here. Well, sorry again, it's not the solutions that are only the answers. Okay, so there are our 8 problems there, and just check your answers to those. Okay, well, you can toggle back and have a go. I'm going to go on now. And here we are. I promised you some in sign of a quadratic nature. There they are. I think this one you don't have to factorise like that. You can just divide both sides by 4 and then find the square root. Remember, when you're solving something like sine squared x equals some value, let's say it's a quarter. Now just remember, sine x, it's a quadratic. It's plus or minus a half. Don't forget that when you're simplifying that one there. You can move terms across the other side and just do the square root of both sides, but just check that out. These other 3, you'll need to use the quadratic factorisation as I showed you with cos x. Alright, have a go at those. Same thing. I've got the answers down below here, so you can come down and have a look in a minute. Okay, so there they are. Okay, and go back and forward and check your answers. Alright, are you ready to move on to greater heights? Let's have a look now at what we can do. Here's a tan set here. Did you forget about tan? Well, here they are. Okay, hence solve these equations. Now, it says solve it in terms of pi only. That means the exact solution, so you can't use a technology, a calculator. And I think what we'll do is we'll put these on this domain, the exact solutions of that. So we're only using one here. So they're saying get the working angle basically here for tan x equals root 3. So you're going to have to remember your sine and cos values, divide them out. So that's just a little group of tan functions. Do it in exactly the same way. Just remember though, tan has got the period of pi. So when you do your solutions, it's going to be plus k times pi here. Okay, k times pi. So just check that one out. Alright, have a go at those and come down, here we are, to the answers. And you can see they have written the answers this time in terms of k pi. Okay, so you might try to use that from 0 to 2 pi. Because we don't actually have to write the general solutions in this course. We'll actually just keep rotating around the circle and list down the actual values for that one revolution. Alright, well finally now we have one of the main purposes of doing solution of trig equations, and that's something like this. As I said before, if you are modelling, finding a mathematical description of a practical situation, that's what modelling is, then you might have this for heights above mean sea level with time of day here, time hours after midnight. And so what we're trying to do is to see what the tide is doing using our mathematical model. It's periodic because, as you know, so we have sine, so it's a periodic fluctuation, tides. And so let's graph the thing for a start. So using technology, we would then use Shift F5 and G-solve to get the key points here. So I think you're probably these values here, you know, the maximum and minimum values, get those right, get a nice shape, and end up in the right point there. Notice the axis here. The axis is not degrees, cannot be degrees. It's effectively radians, because that is a ratio which hasn't got units, and that's what we want to use for time, because the 0 to 24 can't be measured in degrees. We're going to use the unitless quantity or ratio, which is called radians. So you have to set your calculator up if you're going to do this with technology and then put it on your answer sheet. Have to set it up in radians. So just watch that on the calculator that it's set with the Casio, that shift menu to go to setup, and then scroll down to angle. Remember this, and make sure it's in degrees. And of course, if you're graphing, you need Shift F3 as well, because that's going to give you your view window, which has to be adjusted. Okay, also in radians. Okay, so what are the questions here? When was high tide, and what was the maximum height? So that's points A and B there. Let's go down and see if we can do that. So high tide is at 3 a.m. and 3 p.m. So you're just reading that off a technology graph using G-solve for maxes and scrolling across to the second one. And what is the maximum height? Well, that's this value here. So if you do Shift F5 on the Casio to G-solve, you will get both the X values and that Y value up there. All right, what was the height at 2 p.m? At 2 p.m, again, using G-solve, 2 p.m, T is 14 hours after midnight. So we would go Shift F5 to G-solve, and we want a Y calc when an X is 14, and we would get this value here. Now, we could actually do a couple of things here. If we were asked for the exact answer, we would have to put 14 in our original function, and that's what they've done here. Well, that's not going to be the exact answer. We'd have to leave it in pies here. Oh, that's 2. What is that? 2 times pi and 3. So we could actually get that as a third if we're asked for the exact answer. So we'd have to do that if they asked us for that. What else might we want to do? Well, let's have a look at this last one. If a ship can cross the harbour, provided the tide is at least 2 metres above the mean position, so that's this. So we'd want the height there to be 2, and you could try to do that with technology, with G-solve again. Or, here we are, if they asked for it exactly, we would perhaps have to do this. Okay, now this can't give us an exact solution, because as you can see here, sine would be 2/3. And so that's not a common working angle. So we would use the technology way, graph 2 and graph the function and find the points of intersection. We have to watch it though in the paper. If they asked us, for example, something like 3 sine pi t on 6, and that was equal to, what can I have? Something like 6, it wouldn't make much sense in this one. because then oh no, let's make it, what could we do? 1.5? Let's do 1.5. Because then if I divide both sides by 3 here, I would have 0.5. Now that is a common working angle, and we could get exact solutions. So it wouldn't be acceptable to do it with technology if they gave us that and asked for exact solutions. Okay, so just watching that. In the problems where we're tempted to use technology, just watch that they don't ask for exact answer. And up here, I wonder if we shouldn't unpack this a bit. When we draw the graph, they're not actually asking that. What is the period? We've taken all these points from the calculator, but do we understand this, the period? So do you remember here, the number in front of the angle variable there, pi on 6, is equivalent to the number of cycles of the function in 2 pi because of that stretch. Okay, so what does that mean? The period, if we were asked for that, would be 2 pi divided by pi on 6. Even though it's strange, it looks strange, we can do this. So it's 2 pi times by 6 on pi, which is 12 hours, and that's what we'd expect with tides, don't we? Okay, 12 hours. So that little calculation up there is important for functions when asked for. We actually weren't asked for a statement of the period here. Can you see that that is true? Because starting here in the graph, yeah, we are getting 1 period's worth at 12 there, at 12 hours. So it all works out nicely. Now this sort of problem is what we are mainly aiming at with solving trig equations, even though we've done this particular model mainly with technology. Okay, so let's come down and have a look at some questions where we can utilise technology and other skills and solve equations. So here are a couple here. A species of insect, initial population, smallest and largest population sizes, find the intervals in which the population exceeds 4,000. So that's our equation 1 there. And we would generally use technology for that, because it doesn't say give exact answers. And I think all of these are going to be the same, but we want to graph the function, get familiar with it, maybe look at its period as well. They don't ask for that here, and so on. So these are interesting things, all of these, because the application of our circular functions, or our trig functions, if you like, to everyday life. So it's good modelling. All right, so I want you to have a go at those. I have to scroll down. I'll scroll down in a minute, and the answers are down below. Okay, so there's question 1 and 2. You can pause it and have a go in a minute. And then question 3. And I think that's 4, the complete 4 there. Okay, and let's look at the solution. No, there's 4 there. We've got a couple of other parts on the bottom of that. Okay, and then let's look at the solution, the answers, sorry, they're not fully worked solutions here. So that's 1 and 2. And check that you're getting a good graph there. And question 3 and 4. Check that your graph has got all these annotations, right, and that the key points are in the correct position where you start and finish. And these should be able to be read off fairly accurately on graph paper. Okay, well, congratulations on building up so many skills. We still have a little unit to do to finish this unit 3 off, this topic 3 in the IB Standard Level New course. And that's to do with trig identities, where we use them to simplify expressions. So, for example, we can solve equations. So I hope to see you then. For now, it's cheers from me.